Welcome everyone to another session of the discrete optimization talks. And we're very happy to start today with Simge Küçükyavuz. I'm sorry for butchering that, as usual. Simge is an associate professor at Northwestern University in the Industrial Engineering and Management Sciences Department. She is an expert in mixed integer programming, large-scale optimization, and optimization under uncertainty. Her research has been supported by multiple grants from the NSF, the Office of Naval Research, ONR. She is the recipient of the 2011 NSF Career Award and a co-winner of the 2015 Informs Computing Society Prize. She is the chair of ICS and serves as on the editorial boards of Math of OR, Mathematical Programming, and Mathematical Programming Computation. So we're very happy to have Simge today. She will talk for around 25 minutes, then there will be time, about 5 minutes for questions afterwards. You can also, during the session, put all of your questions in the chat, and I'll write that in the chat as well, that you can put your questions there, and we might interrupt her during the talk or leave them to the end to answer the questions then. So with that, please take it away, Simge.
All right, thanks Alex, and thanks Elias for inviting me. This is really a nice community and we're staying in touch in these interesting times. So today I'm going to talk about distribution robust chance constraint programs with right-hand side uncertainty under Wasserstein Ambiguity. So this is joint work with my distribution robust team, or dream team as I call them. So it's been really a pleasure to work with Nam, who is at Wisconsin Institute for Discovery, Fatma at Carnegie Mellon, and Dabeen at the Institute for Basic Science. So let me start with setting up the notation and the generic chance constraint programming formulation. So capital X is going to be the compact domain for decision vector X. And S of X is a decision-dependent safety set. So this is where we want to be. And C is a random vector with a distribution P star. And epsilon is a risk tolerance for the random variable C falling outside the safety set S of X. So we want this risk to be low. So the chance constraint program minimizes a certain objective. C is a given vector of coefficients. Subject to the deterministic constraints on X, that's given by the calligraphic X. And this chance constraint, which says that according to this probability distribution P star, the probability of falling outside the safety set should be small, given by our risk tolerance, epsilon. So what are the challenges with this chance constraint program? Well, in practice, the distribution P star is often unavailable to the optimizer. And even if it is available, this evaluating P star C not in SX is a difficult evaluation problem. So, so this makes chance constraint problems particularly difficult. So one way around this is to generate capital N many IID samples and approximate the true distribution P star with this empirical distribution. We call that Pn based on the sample size, sample N. So these samples are also known as scenarios in stochastic programming. So a finite number of scenarios and a discrete distribution to approximate the true distribution. So with that, we can write a sample average approximation of a chance constraint program. So again, same objective and deterministic constraints, but we approximate the chance constraint program with this chance constraint corresponding to the empirical distribution. Here, one is the indicator function. So we look at the scenarios that are outside the uncertainties, the safety set, and then multiply that by this probability 1n, 1 over n, and make sure that that's less than our risk threshold epsilon. So it's well known that for certain safety sets S, this can be formulated as an MIP. Oftentimes it's a mixed integer linear program. But what's observed is that the optimal solution to this SAA, when tested out of sample, can result in high variance. It's very sensitive to the specific sample that we have, and it doesn't work as well for small n, so small sample sizes. So we'd really like to have larger sample sizes, which makes this problem difficult to solve. So one way to remedy this, again, this has been proposed in the literature, is a paradigm called distributionally robust chance constraint programming. So in this DR-CCP, we replace that complicated chance constraint or its empirical approximation with the following. So here we look at all probability distributions that are somewhat close to our nominal or reference distribution Pn. And that is determined by an ambiguity set, Fn of theta, and theta is a parameter that governs the size of this ambiguity set. So among all these distributions that are within the ambiguity set of distributions for the given parameter theta, we look at our worst case probability of being unsafe, and we want that to be less than or equal to the risk threshold. So this is the definition of a distribution robust chance constraint program. So now I need to specify the particular ambiguity sets that we're looking at and the safety sets that we're considering. So in this work, we consider Wasserstein ambiguity set with radius theta. So this is defined as all probability distributions that are within theta distance to the nominal distribution Pn, where the distribution is measured as a Wasserstein distance. So the precise definition of the Wasserstein distance is in my slide over here, but I'll give an intuitive description. So we have our discrete distribution Pn, that's like this histogram over here representing the discrete distribution, and we look at the red distribution P, and it's the, it can be thought of as minimum cost in terms of the distance to move P towards Pn. So with that definition, we define a Wasserstein ball of radius theta that are distributions that are within theta distance from the reference distribution. So that's the ambiguity set that we consider in this study. Later on, I'll also talk about the concept of a distance to the unsafe set. So this is defined for any safety set S of x as follows. Given a decision X and a realization C, the distance from C to the unsafe set is again given by this formula. Again, let me just describe the intuitive definition. So this gray polyhedron here is S of X for a given X. And say we have three samples, C1, C2, C3 scenarios. And the distance of C1, so what is safe is inside this gray polyhedron, and the distance of C1 to the unsafe set is this distance given by this length of this blue line. So the shortest distance to the unsafe set. Note that this is also decision dependent. I have a different polyhedron S of X bar with, denoted by these blue polyhedron, and C1 for the blue polyhedron S of X bar is unsafe. It's outside the safety set, so the distance to unsafe set is actually 0. Those are the concepts that I will need. Finally, there are different ways of defining the safety set, and the one that we consider in this work is a safety set defined by linear inequalities with the so-called right-hand side uncertainty. The safety set S of X is defined by all C, such that BP, DP, AP are given data vectors. BP multiplies C and AP multiplies X, and then we have this constant. And I mean, the name right-hand side uncertainty is borrowed from chance constraint programming SAA. So if we move these non-decision dependent terms to the right-hand side, that's essentially where the randomness appears. In other words, C and X don't get multiplied. They appear separately. So this is known as right-hand side uncertainty. So with this definition of the safety set, we can write a closed formula for the distance to the safety set. So distance from C to this particular S of X is given by the maximum of 0 and minimum over all constraints inside the safety set, P in P, of the left-hand side term divided by this dual norm of BP, which is for our purposes is going to be a constant. So it's just a normalization. So again, if this term on the left-hand side of the uncertainty set for any P is negative or less than equal to 0, then we're sort of unsafe, and that means the distance to the unsafe set is 0. So we need to take the maximum of these two terms. All right, with that, Chen, Kuhn, and Wiseman, and Wei-Jun Xie gave a reformulation of distribution robust chance constraint programs. So again, I have the original feasible set given in the first formula, XDR of S, and they showed that this feasible set is equivalent to a formulation in a lifted space with auxiliary variables T and R that are non-negative, some linear constraints, and this red constraints that has to do with the concept of distance to the unsafe set, this function being greater than or equal to T minus Ri for each scenario I. So again, I don't have time to explain this in too much detail, but this really captures, turns this supremum formulation into a formulation that after some massaging, we can enter into an optimization software. And in particular for the safety set that we consider, this distance Ci to S of X is given by the formula that I had shown before. The problem with this is it's a non-convex constraint. We have max of 0 and a minimum of affine functions. So this red constraint is non-convex, but it can be linearized using binary variables. Again, the authors suggested this reformulation. So what we do is we keep the linear constraints, and then for the red non-convex constraint, we replace that with a set of 2 sets of constraints. And these sets of constraints work as follows. So we introduce the binary variable Zi, and Zi is 1 if the minimum over P and P, this term in the distance function is negative. So that's the role of Zi, and this exactly captures what we wanted to capture in the non-convex constraint. So this is the formulation that we started out with, and the authors observed that this formulation is difficult to solve, especially for small theta, small radius in the Wasserstein ambiguity set, and even for sample sizes like 100. And the main culprit, as we all know, in discrete optimization is the weak LP relaxation, the big M's that we have to use in this formulation in order to convexify or linearize the non-convex constraint. All right, so this is our motivation. So to be able to attack this, we have a key observation. This is known, but the way we utilize this observation has led to several enhancements. So I'm repeating here the feasible region of the sample average approximation, that is the nominal distribution, how we capture the chance constraint with the nominal distribution, and the distribution robust feasible region that has to do with the supremum over all probability distributions in the ambiguity set, Fn of theta. And the key observation is that for theta equals 0, the radius equal to 0, the ambiguity set contains only the nominal distribution, Pn. And in general, as we relax this theta, what we see is that you can sort of visualize my picture. Fn of 0 is a subset of Fn of theta. And because we're taking the supremum over all these distributions over Fn of theta, and Fn of 0 is Pn, we can see that actually the feasible region of the sample average approximation is nothing but a relaxation of the distribution robust problems feasible region. So using this observation, we are able to propose our first strengthening of this formulation. So this is the initial strengthening result. What we have in this strengthened reformulation, so that what you see in black is what we had before from the previous research. And what we add on top of these constraints is 2 sets of constraints now in red that represent the deterministic reformulation of the sample average approximation problem. So remember, in the sample average approximation, we have an indicator function whether a scenario is inside a safety set or not, which involves whether the function inside the distance function is a negative or not. And so we can add the same types of constraints with a 0 right-hand side with the same binary variables. So what's important here is that the Z variables are exactly the same Z variables as we used in the distance function constraint. So no additional variables are necessary. And we add this set of constraints that represent the feasible region of a sample average approximation. What's more important is this cardinality constraint on the Z variables, which how many of them can be one at a time. And that's essentially given by the quantile. So epsilon n rounded down, many Z's can be one at the same time. So this is already an initial strengthening of the reformulation. So we took it from there and observed many other enhancements. So I'm limited in how much I can go into detail, so I will not be able to give all of these details. I have backup slides if anyone is interested, but I'll give this sort of visual representation of all the other improvements we were able to do. So this red one, SA for CCP, stronger formulation, is the one I was able to show. Once we have that, we can actually improve the BGAM using quantile information, and that brought about important improvement into the current formulation. Then we can do what is typically done for SAA for CCP, mixing inequalities and their strengthening. So that was sort of first step by making the connection to sample average approximation. Then Wei Jun had a very nice observation, an interpretation of a formulation using the conditional value at risk interpretation. So that allowed us to give some variable bounds. I had this auxiliary variable T, and with the CVAR interpretation, we can see that that T is nothing but a value at risk of the distance for the nominal distribution. So with that, we can put some bounds on it. With those bounds, we were able to reduce some of the constraints because we noticed that they are redundant. And furthermore, we ended up with a robust, so-called robust substructure, a substructure that arises in robust 0-1 programming, for which some valid inequalities were proposed in the literature called path inequalities. So we're able to sort of deploy all of these tools. These are seemingly different paradigms in sort of uncertainty modeling, but all of them have some connections to the distribution robust chance constraint programs that we were able to exploit. So again, I'll flash at these slides, but I can come back to those later, showing all the details. But just go over what we end up with. So this is what we end up with. We call it the strengthened compact formulation. So first 3 sets of constraints is what we had before. 4th constraint is what we had before almost, but I'm specifying here a big M value that is significantly smaller than what was proposed in the literature. QP has to do with the quantile that I have a precise definition, which I can show later. What's also different here is that instead of writing it for all samples, we are writing it for a very small subset of these samples. So this is again, epsilon n many constraints that we need, so significantly smaller. We have this constraint that is inherited from the sample average approximation strengthening. And this last constraint is what I was talking about in terms of the variable bounds that come from the CVAR interpretation. So a whole bunch of tools that we are able to use to strengthen the formulation. So with that, I will summarize the resulting sort of performance of all of these improvements. We tested this strengthened compact formulation and some of the valid inequalities on the distribution robust chance constraint transportation problem. This is the original study of Chen et al. This was the one set of instances that had the right-hand side uncertainty. So this is a sort of a classical transportation problem with some uncertainty introduced. We have a set of factories F with deterministic capacities, MF, and we have a set of distribution centers D. They have random demands, CD, and would like to meet the random demands with high probability at minimum cost. So, so almost a classical transportation problem, except for demand satisfaction constraints are written in a probabilistic fashion for all probability distributions that are in this F theta. We took 5 factories, 50 distribution centers, risk tolerance 0.1. We started out with the radius of theta 1, 0.001. Then we tested 9 more radii. So theta 2 is going to be something larger than theta 1. And theta max is a parameter that ensures feasibility. So the maximum theta that makes the problem feasible. So we varied different theta in increasing values. In our preprint, we have a more detailed analysis, but in this presentation, I will only have time to compare 3 formulations. One is the basic original formulation given in Chen et al. The other one is the improved formulation that I showed, the final version, the strengthened compact formulation. And then I alluded to two classes of inequalities, mixing inequalities and path inequalities, that we could generate because of the substructures involved. So mixing plus path will be the strengthened formulation by including the mixing and path inequalities. So again, this is just a summary. We have the full results with all theta in our paper. So we started out with n equals 100, but because this was even difficult for the basic formulation. So what I report here is just the 3 theta values. I will report time if all the 10 instances we tested per setting was able to solve within the 1 hour time limit. Otherwise, we'll report gap if the gap is available. That means we found an integer feasible solution. And in the superscript F and D, we report how many of the 10 instances was actually able to find an integer feasible solution. So for theta 1, this is the smallest theta, 0.001. This problem is very difficult. It's almost like a SAA for chance constraint programs. So none of the instances were solved by the basic formulation, but all of them found some integer feasible solution, and the end gap is about 1.16. Whereas in improved formulation, we solve these in a few seconds. And adding mixing path inequalities help, but the problem is so easy now that it actually slows down, the separation process slows down. So it may not even be necessary for these types of problems. The problems get easier for all formulations as we increase theta, but still improved formulation works much faster than the basic formulation. So then we wanted to push the sample size. So we tried n equals 3000. Again, we have the full set of runs from theta 1 to theta 10, but I'll just show you the first 5. So here, of course, the larger size problems, a lot more difficult for all methods. What we notice is theta 1 is really difficult. So this time basic is not even able to find any integer solution. We cannot report for the 10 instances. So we can't report any gap information within the time limit of 1 hour. We also hit the time limit in all 10 instances, but we have a very small end gap. And mixing and path inequalities start becoming useful for these instances in terms of reducing the end gap, and we're adding a few thousands. What's interesting is we are not adding mixing cuts as we increase the theta, and that's sort of expected because theta equals 0 is sort of when mixing inequalities are mostly used, and when theta is close to 0, they are still useful, but as we relax theta, they don't get generated. As we increase theta, the problems are getting easier, but again, 5 instances did not even find integer solutions for the basic formulation. The end gap is 69 for the other 5, whereas we solve these problems. We find integer feasible solutions to these problems with very small end gap. And once we reach theta 3, these problems are easy for the strengthened formulation, but the basic formulation still struggles. I think as we increase theta further, basic was also able to solve these problems, but we're able to solve them much faster. I think I'm running short on time, but some insights into why the n equals 3000 instances are difficult can be understood from the root time and root gap. So for basic formulation, a lot of time is spent at the root node, and the root gaps are very high for the small theta instances, whereas improved formulation from the get-go reduces the root gap quite significantly and doesn't take too much time to solve. Mixing and path, obviously, again, because we're separating at the root node, we spend more time at the root node for small radii. So with that, I'll end with a summary of contributions. So we proposed an advanced formulation of distribution robust chance constraint programs that exploits connections with various models of uncertainty. We use the nominal SAA relaxation of chance constraint programs, conditional value at risk interpretation, connections to robust 0-1 programming. And with all these enhancements, we're able to uniformly reduce solution times by at least an order of magnitude for all the radii that we tried, large number of scenarios and so on. Our preprint is available. I think it's also linked from the workshop website. And coming to a Zoom near you one day, or maybe a real conference, is left-hand side uncertainty. So there are some significant differences between the right-hand side uncertainty and left-hand side uncertainty. And this is something we're working on right now, and we should have something available pretty soon. All right, I'll end there.
Thank you, Simge. That was a nice talk. And we can now take any questions. If anybody has any questions, you can either raise your hand through the participants panel, I believe, or you can put it in the chat, and we will, Simge will either read it or I will read it to her. So if you have any questions, please go now. Ah, yes. Go ahead, Paul.
Oh, nice talk. One question, did you ever look at using combinatorial Bender's cuts instead of the big M's?
Oh, we haven't looked at decomposing the problem yet, so, or like thinking of it in a Bender's fashion, mainly because, you know, we found our way of finding big M and the strengthened formulation very strong. But yeah, as we scale these things up even further, decomposition methods and the cuts that come along with it, like you mentioned, might become more useful. So that's something we can look at. Thank you.
Are there any other questions from the audience?
Something in chat box?
Yeah, do you see it? Could you read it just in case the recording doesn't
oh yeah.
chat?
So it's from Truian. You use the Wasserstein distance of order 1, that's true. What's the role of that special cost? Is it interesting to consider other cost functions? Yeah, so I think for tractability, we use the Wasserstein distance of order 1. So the cost is essentially the distance. We haven't considered higher orders. That's something we can definitely consider. It's typically order 1 distance is considered, or at least in the previous literature, this is what was considered. But yeah, this is a good question as well. Something to think about.
And there will also be time after this next talk for more questions in a more in a smaller setting, basically, and for socializing, of course, as well. So maybe we'll take any other questions to that subsequent section. And now I'm going to end the recording for this part.